All right, my shots. Okay. So exam, next time I see you, we are right here. So what I'm gonna do, because we're not gonna finish chapter 5, is chapter 5 will be moved over. Oh, I'm not in where I can edit it because I'm not signed in. It's gonna move to Wednesday because we're not gonna finish it today. But whatever we finish today will be on the exam. Whatever we finish today will be on the exam.
So we're not gonna finish chapter 5, but whatever we cover on chapter 5 still will be really long.
Correct. We are not going to finish all of the material for chapter 5 today, but all of the material from chapter 5 that we covered today will be on the exam. So your exam will be chapter 3, chapter 4, and everything we cover up till the moment you walk out the door today in chapter 5. Yep. But the homework itself is due next Wednesday because we're going to finish
Are
it.
we gonna go over the rest of chapter 5 next Tuesday? So we can finish
Yes.
the homework?
Yes, yes, yes. There won't be that much left because we got very close to finishing last class. We just didn't get to the very end.
Would you know the numbers on the homework that like aren't gonna be on our site, so that way like we can do this to be able to practice this stuff?
They scramble them. I can't tell you because your numbers are going to be different from her numbers.
Okay.
You know what I mean? But you can also look at the end of the chapter too, and they go sequentially by section. So the end of chapter questions are sequential by sections.
Okay,
So if you want some extra ones where you have the answer, you can see those too.
okay.
But you'll be able to see which ones we haven't covered yet in chapter 5. You're like, oh, we didn't cover that yet.
Okay.
Yeah. All right, any other questions before we start? So exam, next time I see you, bring your calculator, bring your pencil. I provide exam, answer sheet, and best friend. So when you sit down, there should be nothing at your desk. You'll just have a pencil and a calculator. Okay, good. You do need to bring your IN number. You need to know your IN number because you have to put that on your answer sheet. Okay, so make sure you know your IN number, or like you have it on your phone, you can write it down and then pick up your phone. Okay. All right. So make sure you did your seating chart. Oh, and this is the other thing I wanted to say. If something happens and you end up having to take an exam online for whatever reason, it's not going to be the way that it was for the open book exam. It's going to be on Moodle, and it's going to be in a lockdown browser called Respondus, and it will be monitored with a webcam. So you'd have to take the exam on a computer with a webcam. But this is only if you're on quarantine, whatever it is, right? But something where you physically cannot come to campus. But if you have to do that, I provided you all this information on how to use it because you have to download the Respondus application. And then I gave you a practice exam, but it's a pretend exam. It doesn't count for points. It's like, what is 2 + 2? You know, and it shows you how to get to your best friend within the exam and all that kind of stuff. So it's really there just so that it's not the first time you've had to deal with the program when you go in and try to take an exam online. Okay. Any questions on that? Okay. And I'll leave that up for the whole semester. Okay. So now, y'all ready for some eye clicker? Get your eye clickers out. Get your eye clickers out. Okay. Everybody ready? All right. In a general chemical equation, where are the following 3 components located? First, second, and third. So you just have to put them in the right order. I'll give you 1 minute. Oh, and I didn't do a joke. After this, I'll do my joke. Some of y'all were like, yeah, we got away without a joke. No, I'm still going to torture you. I'm closing it at 1 minute. Okay, 10 seconds. Okay. Turn and talk to the people around you. Buzz in one more time. I'll give you 30 seconds. Make sure those masks are covering your noses. Closing it at 30 seconds, so don't forget to buzz in for the second time. 10 seconds left. It's a good, easy one to get y'all started, right? All right, so what did we say? Good, very nice, very nice. So let's go back. We almost had 100% on the very first one. That would have been awesome. All right, so whenever we're doing this, right, we say reactants, yield, products, right? So it's the reactants first, the yield sign second, products last, right? Okay. In an exothermic reaction, heat blank. An exothermic reaction, heat blank. Okay, 10 seconds. Okay. Turn, talk to somebody, see if they have the same answer. Some people in chat can chat. Give y'all 30 seconds. Make sure you buzz in a second time. I think we had 38 people. So make sure you buzz in a second time. Okay, 5 seconds. Okay. So what did we say? In an exothermic reaction, heat is given off. Awesome. Heat is given off. Great. So I was really nice in this. So y'all are right. Give it off in the reaction. Because when I said exothermic always refers to what? Thermic tells me heat, right? I could have had answer choices that said heat is given off, energy is given off, right? Be very, very careful about that. If I had said not exothermic, what would I say for the energy equivalent of exothermic? Exergonic, right? So be very, very careful about that. On the exam, you will have answer choices like that. So I'm trying to give you a heads up now. Cover your nose, please. You will have answer choices like that. So if you see delta H, that's not necessarily exo, but it's thermic, right? Delta H is thermic, and that's heat. Okay. All right. So now you kind of have to apply what we just talked about. In an energy diagram for a reaction, the products are shown at a higher level than the reactants. What must be true about this reaction? Very careful about this one. You might want to draw an energy diagram. Wouldn't be bad. Don't forget to buzz in. 10 seconds. Okay, don't forget to buzz in. All right, turn and talk to the people around you. Turn and talk to the people around you and buzz in again. Still hear people talking, so keep talking is what I'm saying. Keep talking. I'll give y'all till 1 minute. Okay, y'all ready? Make sure you buzz back in or what? Click back in. I don't know what that is. All right, here we go. So what did y'all say? All right. Very nice, very nice. Okay, so we went up a lot. Let's talk about this. If I drew an energy diagram, what would my energy diagram look like? What goes at the bottom? Reactants going to products. So I read this, the products are shown at a higher level. That's why I like to write it at the bottom. My products are shown at a higher level than the reactants, right? So I'm going to draw my little curve with a little bump. What must be true about this reaction? What's this axis here? Energy. Is it heat? So can you answer anything about heat? You should have eliminated those two answer choices right off the bat. Okay, that's what I was just talking about in the last one, right? I told you I was gonna do that. Okay, now, in order for me, remember you're gonna picture me, right? This is gonna be me and I'm on my bicycle. Am I happy about climbing this hill? No, I am very sad, right? I'm very sad about climbing this hill on my bicycle. Why? Because it takes energy in order to get to the products. So the reaction has to absorb energy to form the products. Another way to say that is you would have to put energy in to reach the products. It's the same thing. It's just worded slightly differently, right? So the reaction must absorb energy to form the products. Can you talk about potential energy? Not really. Technically, you could. If this is a high potential energy, this is a low potential energy. So your potential energy has actually increased. So, and then we really haven't talked about stability yet. So we shouldn't talk about that yet. Okay, cool. All right, let's do one more. I think I have one more. Yeah. Okay. Select the correct statement regarding the reactions represented by the energy diagram. So we have two. This one's A and this one's B. So select the correct statement regarding the reactions represented by the energy diagrams. Ten seconds. Okay, turn and talk to your neighbors and then click in again. Cover your mouths and noses with your mask. I'll give you until 1 minute. It's a good discussion. Don't forget to click back in again, 10 seconds. Don't forget to click back in again. Okay, so which ones could you immediately eliminate? A and C. A and C. I'm crossing out the wrong ones. Hello. A and C. Is it Monday today? So we know that we're not talking about heat, right? So we immediately eliminate heat. So now it's either which one of these is slower? Is A slower? Is B slower? Or are they equally fast? So I want you to picture me, there's me, on the bike, right? Which one would I rather ride? I would be much happier riding B than I would be riding A. Which one would I be able to ride faster, get to the top of the hill faster? B, right? So reaction rates, and we're going to talk about this a lot more today. The less energy that you have to put in to make the reaction go, the faster the reaction goes, right? Because it doesn't require a lot of energy to get to a product state. So the less energy you put in, the quicker you get there, right? So sometimes I'll have, so the reaction rate for A is slower. So A is slower. So let's grade that. So B, A is slower is B. Gosh, that's confusing, huh? Okay, so y'all are at least really between B and D. So you were on speed. So that's good. That's good. We're making progress. Okay, so let's switch over to our practice problems, our in-class practice problems. Okay, and we were right here. We were talking about what we were going to eat, right, for breakfast. And I forgot my jokes. Okay, so what do you get when you cross a turtle and a porcupine? A slowpoke. And so Charles had 2 today. What kind of pants do clouds wear? Thunderwear. Thunderwear. He really liked that one. All right, so what we're going to do today is we're going to take a meal. We're given breakfast where we have 2 eggs, 2 pieces of toast buttered with a tablespoon of butter, and a 6 fluid ounce glass of orange juice. And what we're going to do is we're going to be able to figure out how many calories are in this given meal. That's what the question asked us for, calories. Now, remember how at the very end of class last time, I had you write down calories, big C calories, nutritional calories versus calories, which is the chemistry one, and then joules. So I could ask for the answer to this kind of a problem with any one of those 3 units. So we'll talk about how to convert that at the end. So if I were to give you this kind of a question on the exam, I would give you this table, but I would not give you this column. I would not give you that column, but I will give you this. So I'll give you this and I'll give you this. So we're going to solve the problem as if you didn't have this last column, because it would be a whole lot easier if you did. But I'm not going to give that to you. Okay? Because no nutritional label ever gives you that. No nutritional label gives you that. It gives you the grams of each. Okay? So this is real life. So we want to know how many big C calories would be found in a breakfast consisting of all this stuff. So if I have eggs, what I'm going to do is I'm going to go up to my table and I'm going to say, okay, here are eggs. In 1 large egg, I have 0.6 grams of carbs, 6.07 grams of protein, and 5.58 grams of fat. So then I just put that in here. But what do I have to do to that? I have to multiply it by 2 because I'm having 2 eggs. So it's 0.6 times 2 is 1.2 grams. Right? This is how many grams of carbs are in 2 eggs. How many grams of protein? 6.07 times 2 gives me 12.14 grams. And then do your fat. Your fat we said was 5.58 grams times 2, and we have 11.16 grams. Does it make sense that eggs don't have a lot of carbs, but do have proteins and fats? Proteins are in the white, fats are in the yolk, right? So that makes perfect sense. Okay, now you have to call out the answers to the rest of them. Toast, 2 slices of toast, how many carbs? Go find toast. 14.1, but I'm going to multiply that times 2 because I have 2 slices of toast and I get 28.2 grams. Okay, how about protein? How much protein is in toast? 2.4 grams times 2. We're going to get 4.8. Okay, fats, how much fats? 0.9, and we're going to multiply that times 2, and we're going to get 1.8 grams. Does it make sense that toast is mostly carbohydrate? Absolutely, absolutely. Okay, butter. What is butter going to be mostly? Mostly fat. Okay, so how many carbs? And we're 1 tablespoon, so make sure that that conversion is correct. So in 1 tablespoon of butter, how much fat? How much carb? I'm sorry. 0.8 grams, so not very much at all. How about protein? 0.12. And then how about fats? 11.5 grams, so mostly fats. Okay, orange juice. Orange juice, they gave it to you in 6 fluid ounces. You have to be able to convert because the table gives you cups. It doesn't give you fluid ounces. So you have to convert fluid ounces to cups. I did it for us. 6 fluid ounces is the same thing as 0.75 cups, right? So if you're given, say for orange juice, it says you're 27 grams of carbohydrates. To get that for 0.75 cups, you just multiply times 0.75. What do you get? I got 20.25. I should hear some calculators clicking. The beautiful, beautiful sound of clicking calculators. It's magical. Okay, so how about proteins? How many grams of protein in orange juice? 2, not too much, times 0.75 gives me 1.5. And then how much fat? 0. Okay. So now we have to total up. We've got everything we've eaten, right? So we need to total up the grams, the total number of carbs, right? So this is total carbs. How many grams do I have? Add up everything in that column. What do you get? What do you get? Mass over noses, please, everybody. I got 658. So do you want to round at this point? It's a good question. No, because we're not, don't round until the very end. So this is how many carbs I have. How many, is it protein next? Protein and fat. So how much protein? Okay, and how many fat? Got like 24. 4.46. Okay, so now, was I asked for grams in the problem? What does it say? I was asked for calories. So it's always nice to kind of circle that in your question, right? You can write on your exam, circle that how many calories. So if I come down, I need to convert these grams to calories. How do I do that? I need a conversion factor that has grams on one side and the big C nutritional calories on the other side. Do I have that? Yes, I do, right? If you scroll up to the very top of that page, I have these little conversions right here. I can convert from grams to calories, or I can convert straight from grams to kilojoules. So if I ask this question, instead of asking for calories, if I ask for kilojoules, what could you do? Just use these numbers instead, right? So always pick the conversion factor that you need for the problem. So for this case, I want calories. So I know that in carbohydrates, there are 4 calories per gram. Protein, I have 4 calories per gram. Fats, I have 9 calories per gram. So I'm going to come down and use those conversion factors. I can scroll down. So I know I have 4 calories in 1 gram. And I don't have enough room, so I'm just going to go down with my answer. So about 50 times 4 should be about 200. So what do you get? Don't round. 0.632. Yeah. Okay, protein, I'm going to do the same thing. Now, carbs and protein have the same conversion factor, 4 calories per gram. So my grams cancel, and I'm left in calories. So how many calories do I have from protein? Grams. Oh, not grams. I'll keep going. Keep wanting to say grams because we were in grams. Calories, right? And then how much do I get from fat? This time I have 9 calories in 1 gram. My grams still cancel. And what do I get? 220.14. Okay, so now how do I get my calories for my entire meal? Just add them all together. And what do I get? Calories. Now, do I have that many significant figures in my original values? No, right? How many significant figures are in my original values? 1. So round this number to 1 significant figure. What do you get? 500. So my real answer is 500 calories. That's my final answer.
So answers are gonna come out to be like somewhere near like 100.
Well, yeah, you got to think this is a regular meal. How many calories? You have a 2,000 calorie diet, right? So 3 meals a day. Breakfast is probably going to be your smallest caloric. Well, it depends on who you are, you know, for like a big breakfast, but right, it's got to be somewhere in there. So if you think about what it kind of should end up being, then you can kind of predict your answer, but you'll have a harder time predicting if I ask you like kilojoules instead of calories. So, but if you've got calories, could you do a dimensional analysis and get to joules? Yeah, because I know that's a nutritional calorie. How do I convert from nutritional calorie to chemistry calorie? What's my conversion? It's on your best friend. Go look. What is it? It's 1,000, but 1,000 chemistry calories or nutritional? 1,000 chemistry calories in 1 calorie. And then if I want to get to joules or kilojoules, let's say I want to go to joules. I'm going to put calories on the bottom and I'm going to put what on the top? Joules, right? Or is it kilojoules? What are you given in the Okay. Let's keep trying this. Internet keeps going in and out. This is going to be a disaster to have to post onto YouTube because it's going to be multiple files. I hate when that happens. Okay. The rest of today, we're going to talk about different parameters about chemical reactions. And the first thing we're going to talk about is kinetics. Now, I like to use a little analogy before we talk about chemical reactions, right? Kinetics are all about how fast or how easy something happens, right? So let's just use cars on the road as an analogy. So if you are driving in New Orleans, heavy traffic, what is very likely to happen? An accident, right? How many times in heavy traffic do you see an accident? Pretty regularly, right? So the more cars that are on the road, the more accidents happen. So accidents are analogous to things that have to happen in a chemical reaction. In order for a chemical reaction to happen, molecules have to have accidents. They have to collide with one another. Now, they have to collide with one another in a particular orientation in order for that collision to be productive. And they have to collide with enough energy. Otherwise, it's a fender bender and everybody keeps driving, right? If you ran into somebody nice. But in order to change from a reactant to a product, you have to collide with high energy and in a proper orientation. That's the only difference, really. So if we have more cars on the road, we have more collisions. What about if cars are driving fast versus slow? Which one's going to have more collisions? Fast. How can we relate that to a chemical reaction? What is it when molecules move fast versus molecules moving slow? Right, if they're moving fast, they're more likely to bump into each other, but I can measure how fast particles are moving. What do we call that? Close. Not the measurement. You can't measure kinetic energy. It's there, and you're right. What can I measure? I heard it. Temperature. I can measure temperature, right? The higher the temperature, the faster the particles are moving. The lower the temperature, the slower the particles are moving, right? So we can talk about things that affect chemical reactions like temperature. If we increase temperature, we increase the speed of those molecules. The faster they're going, the more likely they are to hit one another. The more likely they are to hit one another, the more likely you are to have a productive collision and therefore increase your reaction rate, right? Same thing is true about number of cars on the road. Number of cars on the road is like concentration, right? So if you had a particular space where collisions could happen, if you only have a few particles, are they likely to bump into one another? If you have mostly empty space, no. But the more particles I put into my container, the more likely they are to hit one another. So when we talk about chemical equations, we talk about concentration. So have you ever seen brackets? If you put brackets around anything, like if I did this, this would be concentration of reactants. Yeah, so you'll see me do that kind of for the rest of the semester. Whenever I say concentration, I'll just put brackets. It's what chemists use. Okay, so all those things increase our rates of reaction. Now, do you remember how I said there are two parameters that are important for making a chemical reaction occur? That the molecules are in the right orientation and that they hit each other with enough energy. That energy that is required in order to make the reactants progress to products is called the activation energy. So let's try to make a scientific definition for activation energy. Okay, so describe activation energy for a chemical reaction. Activation energy is the minimum amount of energy required to make the reaction go, but that's a terrible way to say it, right? So let's try to think of a more scientific way to say this. It's the minimum amount of energy required to overcome, and it's called the energy barrier. the energy barrier between reactants and products, right? Because each given set of reactants and products has a unique energy barrier. So some it will be a lot of energy that's required, some it will be not so much. So now, let's say I have a reaction. I'm going to come down here because I just want some place to draw. Okay, I have this energy diagram. Goes from reactants to products, and what's over here? Energy. Let's just say I have something that looks like this. Okay, do you want to be at the bottom of that hill? Absolutely not. That would suck, right? I got to put a lot of energy in to make that happen. So I can't change my starting point for my reactants, and I can't change my end point for my products. What could I change? The amount of activation energy. So where on this diagram, if I had to put a point on it, where is the activation energy? It's the minimum amount of energy that is put into the reaction to turn reactants into products. Right here. This, how did I do that? Right here. On the graph, right? This would be the activation energy. So we call this EA, E sub A, activation energy. So if I could somehow reduce my activation energy, so let's say I was able to do that. I still have to start at the same place. I still have to end at the same place. But what if I did that? Now where's my activation energy? Much lower, right? If I look right here, it went down. So I was able to reduce my activation energy. What can do that for me? Catalysts. Catalysts. So the black curve, let me do this. The black curve is plus catalyst. The blue curve is minus catalyst. Your catalyst could be an enzyme, which is biological, or your catalyst can be like a metal surface that allows a place for the reactants to interact with one another, right? So it could be a bunch of different things, but what do catalysts do? They reduce the activation energy. So catalysts will reduce the activation energy, or EA. So tell me, which hill do you want to climb, the blue hill or the black hill? I'm signing me up for the black one, right? Okay. And that's the whole point of a catalyst, is to reduce the activation energy that's required to make a reaction happen. Because lots of reactions have high activation energies, and if their activation energies are too high, they won't happen. So we have tons of enzymes inside the body that make that a possibility. Okay, so how does adding a catalyst increase the rate of a chemical reaction? If you add a catalyst, what happens? Reduce the activation energy of the reaction. So just stomps down that hill, makes that hill just a little bit more manageable. But a catalyst can only do so much, right? Can only do so much. Okay, so slow chemical reactions have, and I want you to pick either high or low activation energy. High, very nice. High. So if I were to draw something with a high activation energy, I could do this, right? That's a high activation energy. Something with a low activation energy would be something like this, right? Where I don't have as high of a hill to climb. You could do the same thing with a reaction that started with high energy and ended with low energy. Something with a high activation energy would be something that had a high hump and then came down. Something with a low activation energy wouldn't have very much of a hump at all, right? So it doesn't matter if you're starting with a high energy for products or low energy, doesn't matter. You're only looking at that maximum point, at that activation energy, okay? All right, so enzymes are our example of the biological way that we reduce that activation energy. So if you think about enzymes, enzymes are massive. Enzymes are these huge proteins. And these huge proteins usually interact with substrates or reactants that are much smaller than them. So there's only a small portion of the enzyme that actually interacts with its substrate. What do we call that portion of the enzyme? The active site. The active site is the location where what they call catalysis happens. Catalysis is just the catalyzing of the reaction. Catalyzing of the reaction. That's what catalysis means. It's not the whole molecule that interacts with the substrate, it's just a portion. All right, so for this one down here, we want to think about those cars, right? Determine if the following changes in condition would increase or decrease the rate of chemical reactions in which they are involved. Adding a metal surface for two reactants to locate each other. What is this metal surface? What is this? I said enzymes are catalysts, but what else could be a catalyst? Metals, because they provide a surface for substrates to interact with one another. So here, by adding a metal surface, I'm adding a what? A catalyst. So if I add a catalyst, what happens to the rate of the reaction? We increase the rate of the reaction. Why? Because you're lowering the activation energy. You're lowering the activation energy. Okay, B, decreasing the amount of one of the reactants. What are you doing? You're decreasing the concentration of the reactants, which therefore decreases the rate of the reaction. Okay, how about C? Caramelizing onions on a medium-high stove setting versus a low setting. So we're increasing the rate of the reaction. Let's backtrack and let's explain it. So what's this low setting to medium-high setting? What are you doing? You're increasing the temperature. If you increase the temperature, you therefore increase the number of what? Number of collisions, right? The faster something is going, the more likely it is to collide with something else. If we increase the number of collisions, therefore we increase the rate of the reaction. Okay. All right. Now we need to be able to recognize a bunch of different kinds of reactions. So there are three major classes, and let's talk about each one before we try to analyze it. The first class is synthesis. When you synthesize something, you do what? You make something new. So I'm going to take two things, X and Y, and I'm going to make something new. What should I make? X, Y. Absolutely. What's the opposite of synthesis? Decomposition. Good. If I have something that decomposes, how would I write a chemical reaction using the same letters, X and Y? X plus Y. Do you see how they're the reverse of one another? Right? So synthesis and decomposition are just the reverse of each other. Now, the third one is an exchange. So you ever seen like square dancing where people exchange partners? It's the same sort of deal. So if I have, so we're going to call this exchange, right? If I have X, not X, I don't want to do X. Let's not do X. Let's do A and B and C and D, right? What are A and C? Typically, usually, not always, but a lot of times. If I have a chemical formula, a lot of times this happens with ionic compounds. The first letter, the first element is typically a what? A metal. And then B and D are what? D are typically nonmetals, not always. But a lot of times this is what happens. So if I'm going to yield a product, what's my product going to be? I'm going to have a metal and I need a non-metal. So it would be AND plus C and B. And B is in blue, right? Do you see how they swap partners? You had the blues together and the reds together. Now you have a blue and a red and a blue. See how they swap partners? Okay, so that's exchange. Now, there's a particular kind of exchange that happens not with metals and non-metals, but with covalent compounds. And that particular type of exchange, let's see, maybe I can go up. That type of exchange is called combustion. Everyone's favorite reaction, combustion, right? Those are the ones that explode, make loud noises, happen inside the engines of your car. So if you have a combustion reaction, you typically start with a hydrocarbon. What's a hydrocarbon? A molecule with hydrogen and carbons, right? So CH something, right? Okay. And you react it with oxygen and you make two products in a complete combustion. The only products are carbon dioxide, CO2, and water. What happens inside the engines of our car is combustion. Is it complete combustion? If you drive behind a big old truck that puts out a big old black cloud, is that carbon dioxide and water? No, that is incomplete combustion. And you have some other products in there that are not so great for the environment. Not that carbon dioxide is awesome, but plants know what to do with it. So you can have things that have incomplete combustion where they have some other product and carbon dioxide and water, or you have complete combustion where your only products are carbon dioxide and water. But that's how you can recognize a combustion reaction. Do you need to be able to recognize a combustion reaction? Absolutely. Okay, so let's try to categorize these. A, what's happening in A? This is synthesis. Right, we have two individual things turning into one thing. But why do I say that this is one thing in two? Tell me about nitrogen. How many valence electrons? 5, 1, 2, 3, 4, 5. When you have a container of nitrogen, do you have just nitrogen atoms? Are they happy? No, they're really not happy. How could they be happy? How many valence electrons? 5. So what's nitrogen going to do? Make 1, 2, 3 bonds. So you get in 3 bonds and then a lone pair on each nitrogen. So this is an example of a diatomic molecule. The same thing with hydrogen. if I have a container of hydrogen, do I just have one hydrogen atom? No, I got like this massive container of hydrogen atoms. So they stabilize each other by creating a bond. So you get H2, N2. There are lots of diatomic molecules, Cl2, Br2. Those are called the diatomic molecules. So that's why they behave that way. Okay, what about B? What do you see in B? I see a hydrocarbon, carbon and hydrogen, reacting with oxygen to form carbon dioxide and water. So what do I know this is? Combustion. And by definition, combustion must be exchange. Okay, how about C? It's an exchange, right? My aluminum here is going to, over here, is it still with my SO4? No, it went and hung out with the hydroxide over here. My potassium decided it didn't want to hang out with the hydroxide, and it went and hung out with the SO4. So all I did was change the binding partners. So this is another example of exchange. Okay. Questions on that? Okay. Now, here is going to be one of the most difficult questions. No, I'm pretending this is like the easiest thing on the planet right here. This is going to be awesome. So there are some reactions that when they happen, when you transition from reactants to products, you make that product, you can't go backwards and get the reactant back. So things like combustion, right? If you put gasoline in your tank and you combust it by running your engine, are you going to be able to pull those products of carbon dioxide and water and recombine them and make more gas? No. So that is an irreversible reaction. When we write irreversible reactions, we write reactants going to products. It's a one-way arrow. This is irreversible. But there are other reactions that are reversible. So I can have a reactant going to a product, but at the same time, I can have that product going back to a reactant. So I have a double-sided arrow. And so the way that they show this a lot of times is half of the arrow going one direction, half of the arrow going the other direction. So this is reversible. R-E-V-E-R-B-I-L-E. So when you look at a given reaction, all you have to do is look at the arrow. So look at A, reversible or irreversible? Reversible. So I just put an R. How about B? Irreversible. Even if you didn't see the arrow in B, would you be able to make that prediction? Yeah, because it's combustion. You're not getting back carbon dioxide and water. You're not getting it back, and you're not going to be able to put enough pressure to make that happen. Okay, how about C, reversible or irreversible? Irreversible. Gosh, that was difficult, huh? Oh, tough, but I know y'all can do it. All right. The next thing we have to do is we have to do a little bit more balancing of chemical reactions. I know that was one of y'all favorite things to do, right? All right. So the balancing that we didn't do when we were doing general equations and balancing them is we did not balance combustion reactions. And combustion reactions are their own kind of beast. And so it's really good to be good at balancing reactions and then do combustion reactions. And I'm going to tell you a trick. Now, you can balance it just the way you've balanced every other equation, and eventually it's going to work out. But you're going to have the best luck if you balance things in a particular order. So I say you balance in this order. In order, you're going to do carbons, you're going to do hydrogens, you're going to do oxygens. So CHO, you do them in that order, CHO. And if when you're balancing, you get some odd numbers, right? You can get even numbers and odd numbers. If you get an odd number, double everything. And I promise you're going to work. Okay. So those are my two things, balance in order And if you get an odd number, double everything. So if you get an odd number, double everything. Everything. Be careful about that. You gotta double everything. Okay. So write the products and balance the following reaction for the complete combustion of butane. So I have C4H10. I'm not going to write the states of matter just so I have more room. O2, one-way arrow. What are my products? CO2 and H2O. Does it matter which one you put first? No, it doesn't make a difference. Okay, which atom should we balance first? Carbon. So let's do carbon. How many carbons in my reactants? 4. Okay, how many in my products? Only 1. So what do I need to do? I want to multiply times 4 to get 4. So I'm going to put my 4 there. So now my carbons are good. Okay, what element next? Hydrogens. How many hydrogens in the reactants? 10. Come over to my products. Hydrogen is how many? 2, because I have a subscriptive, that's a 2. It doesn't look like a very good 2, but it's a 2. Okay, so I only have 2 of them. Am I balanced? No, what do I need to do? Times 5, so I put my 5 here and I get 10. Now what? Oxygens. How many oxygens in the reactants? 2. How many in the products? Be careful. So look over here. So let's do the oxygen and carbon dioxide first. Oxygen. So I have 2 times 4 gives me 8. Then I have 5 times 1 in hydrogen. I get 5 for a total of 13. You're never going to get, if I come over here, I have an even number here and an odd number here. It's never going to work, right? Unless I do what? I'm going to double everything. So if anything is not there, you assume it's a 1, but we're not going to worry about the oxygen yet, okay? Because we're trying to balance the oxygen. So what's in front of the carbon? 1. So 1 times 2 is 2. So I'm going to put a 2 there, but that changes down here, right? So let's go across. We'll multiply everything by 2, and then we'll go and reevaluate. So we're going to leave oxygen alone because that's the one we're going to be able to change. So now 4 times 2 is 8. 5 times 2 is 10. Okay, now let's go reevaluate. So my carbon on this side, I have 4 times 2 now. What do I get? 8. So I'm going to come over here. Now I have 1 times what? I have 1 times 8, which is 8. Okay, now my hydrogens, I come over here. I have 10 times 2 for a total of 20. I come over here for my hydrogen. I have 10 times 2. So 2 times 10 now. So 10 times 2 is 20. So my carbons check, my hydrogens check. Now let's do my oxygens. Now I'm doing 2 times 8 instead of 2 times 4. So 2 times 8 is what? 16. Okay, then I need to do it for my water. So I have 1 times 10, right? We erased the wrong one. 1 times 10 is 10. So I have a total of how many? 26. Now, 2 times what is 26? So I put my 13. Not too bad, right? So if you go in that order and you follow those 2 little notes, you're going to be okay. All right. So when we've talked about chemical reactions in the past, Everything we've talked about are general chemical equations. But there can be organic chemical equations and there can be biochemistry chemical equations. For all of these general chemical equations, how did we represent them? What do we show? What do we call these? But individually, if I say, this is copper 2 oxide, this is the molecular, what? Formula, right? So that's exactly what we use in general chemical equations. We use the molecular formulas, right? Which is great. It gives you some information. But do you remember how I made you memorize all those functional groups? Right? Well, you're going to have to use them. Coming up real soon, you're going to have to use them. So when we look at organic chemical equations or biochemistry chemical equations, they're going to look like this. Let's see if I can get one that I haven't written all over, right? They're going to look like this. Are these molecular formulas? No, this shows me something about structure. So sometimes it's the condensed formulas. Sometimes it's Lewis structure. Sometimes we want to see just the functional groups that are going to be participating, but we're going to have some kind of structure included in our chemical reactions. Do we have reactants? Yes. Do we have a yield sign? Yes. Do we have products? Yes. So those sort of things are the same, right? List the differences. So both, we have the yield sign, we're going to balance them, but in organic chemical equations and biochemistry, we want to see some structure. And a lot of times what we're going to be able to look at are functional groups within the structure. And looking at the functional groups, we're going to be able to predict what those functional groups are going to do. So that's why it's important that you know them ahead of time, right? Okay. So another type of reaction that you need to know are called oxidation reduction reactions. Have you heard, some of you have heard of these before in high school chem? Maybe a little bit. Okay. So oxidation and reduction talk about the charge of compounds, and it talks about hydrogens and oxygens. So do you see this little key thing I put in? Did I put this into yours? No. Okay. So this is from your book. I don't remember which page, but I'm going to show you an easier way to remember this. But I'm going to tell you that this, I'm going to give you a way to remember it. I'm going to say memorize. And this is one of those things that I would be able to draw on my exam when I walk in the door, right? So I'm going to show you, I'm going to take this away and I'm going to show it. And if you want me to come back to it, I'll come back to it. Okay. But I want to show it how to remember it. Okay. So we have oxidation and we have reduction. Okay. The first thing we're going to talk about are electrons. If we change just the number of electrons, have you actually changed the substance? No, but you've changed its oxidation state. So we have to be able to talk about that, right? We have to be able to say we're not changing substances, but we're changing, are you being oxidized? Are you being reduced? Have you ever opened a banana and left it on the table and come back to it? What does it look like? It's like black, right? It happens really fast because you've exposed that banana to the air. And so there's an oxidation reaction that happens with that banana and the air, and it becomes oxidized. So this is how we're going to determine how things are oxidized or reduced. So I want you to remember oil rig. This is going to tell you about electrons. You heard this, and there are a couple of different mnemonics out there. So if this is not the one you like, it's okay, you can use yours. But this is the one I like because I'm So my dad was in the oil field. I'm good oil field trash. I like it. So oil stands for oxidation is loss of electrons. You just have to remember the of electrons part. Okay. What is rig? Reduction, that's right, is gain of electrons. There are two other ways that you could become oxidized. What letter does oxidation start with? O. So if you become oxidized, the other way that you could be oxidized is if you gain oxygen. Reduction is just the opposite. So tell me what happens with oxygen in a reduction reaction. You lose oxygen. Okay. There's only one other thing that can cause oxidation, and that is the loss of hydrogen. So it's the opposite of the oxygen. So if you gain oxygen, you lose hydrogen. If you're reduction, you lose oxygen. What do you do with hydrogen? You gain hydrogen. And in these two lines, we have replicated what was in that table. But this you could very easily, very quickly write on your exam, right? So rather than trying to memorize a table, have a little mnemonic to make it stick. Okay, did I have a question I had to answer on this page? I don't think so. Okay. So I'm asking here, are the substances shown in italics undergoing oxidation or reduction? So even if you only write one, let's write one. So let's do oxidation. Remember oil rig, so oxidation is, yeah, so oil, OIL, oxidation is loss of electrons. What else? Gain of oxygen, loss of hydrogen. If you write one, you have the other automatically, right? Because the other one's just the opposite. Okay, so let's do A. Silver ions. Now, how do you know silver, the difference between silver and silver ions? Ions are what? Charged. So even if they didn't give you that symbol, you would go to the periodic table and you know aluminum is a 3 and you go on the diagonal, zinc is a 2, silver is a +1, right? Y'all remember that? Okay, so it's a +1. So this is the silver ions. Are electroplated as silver atoms. So how do I write that? Same symbol, it's the same element, but it's changed charge, right? So we went from something that's a +1 to something that is a 0. And so we always put that it's a solid behind it. So tell me, as we move from reactants to products, how do I go from a +1 charge to a 0 charge? Did I gain electrons or lose electrons? So if I'm a +1, that means I have one more proton than electron. So if I go to a 0, that means I have gained an electron, right? Because if I'm a +1 and I gain a -1, what do I get? 0. If I'm a +1 and I lose a -1, that's saying +1 minus -1. Why did I do 3 minuses, right? So minus a negative, what's minus a negative? That's an added. So +1 + 1, I get +2. So be careful with that gain and lose. Okay, I see lots of people get tripped up there. So, okay, so I'm going to erase that. Okay, so y'all just told me I do what with my electrons? I gained 1 electron. If I gain an electron, am I oxidation or reduction? Reduction. I know lots of people look at oxidation and reduction and get scared, but it's not. If you just write down your little mnemonic thing, you're going to be just fine. Okay, B. D-glucose reacts with hydrogen to form the sugar alcohol D-sorbitol. Do you have to know how to draw that? No, you don't. No, you don't. You don't have to learn how to draw that. Just write the words. Let's just write the words in a reaction. So I have D-glucose. What happens to that D-glucose? Reacts with, it's the same thing as putting a plus sign. What does it react with? Do I just put an H? I put an H2. And then what happens? To form, which would be yields, D-sorbitol. So tell me, as I move from left to right, am I going to be talking about electrons? You could, but you don't have to. When I move from left to right, from reactants to products, can I talk about electrons? I don't see electrons. I don't see charges. What do you see? I see the hydrogen. So let's talk about hydrogen. As we move from left to right, what is happening with my hydrogen? It's being used. So basically the H2 is being integrated into the glucose to form sorbitol. So when I go from glucose to sorbitol, what's happening? So this has less hydrogen. This has more hydrogen, right? And so I want to know about this substance. What is this substance undergoing, oxidation or reduction? So as I go from left to right, what happens? I'm gaining hydrogens. So D-glucose plus hydrogens yields D-sorbitol. So D-glucose is picking up hydrogens, and therefore, when it forms D-sorbitol, it's picked up the hydrogens. Now this molecule has more hydrogens. Yes. Because we said hydrogen is one of those diatomics. So hydrogen only has one valence electron. It's really not happy, right? So really you have it in solution with another hydrogen and it wants to form another bond. And so it's going to participate as H2. And you'll see that a lot, but you won't, even if you just put H here, it would have still given you the right answer. Okay. All right, so as we move from left to right, we're gaining hydrogens. So what's happening as we gain hydrogens? Oxidation or reduction? Reduction. Okay, let me erase A so I have room for C. C, the biomolecule FADH2 loses hydrogen, becoming FAD. Do I add something to the FADH2? No. Can I erase the other one? Because I kind of need more room. Yeah? Okay. Oh. Okay, there we go. Okay. So how do I write my reaction? I have FADH2 yields FAD plus H2. Very good. So as we go from left to right, can we talk about electrons? No, what can we talk about? Hydrogens. So what is FADH2 doing to get to FAD? It is losing hydrogens. If you lose hydrogens, what kind of a reaction is this? Oxidation. If I made you go in the reverse, what would the red be? If I said FAD reacts with H2 to form FADH2, What kind of a reaction is that? Reduction. Oxidation and reduction are just opposites of one another. Okay, one more. Then I think we're done with this section, and that'll be a perfect ending point. Okay. All right. Ketone bodies. This is an example of a ketone body. If you ever heard of the keto diet, right? When you go on the keto diet, you start making ketone bodies, which can actually be dangerous if you get too many. So you have to be very careful. So we have a ketone here, and this ketone is being changed from beta hydroxybutyrate to acetoacetate. Does it matter that you can pronounce any of those molecules? No, we are looking for electrons, hydrogens, or oxygens. Okay, you don't have to worry about the rest. Yes, I know it looks like a lot going on, but it's not any different than what we've been doing in the past. So if we look at this beta hydroxybutyrate and our oxaloacetate, how are they different? So here I have an oxygen double bound to a carbon. What do I have here? An oxygen bound to a hydrogen, right? Where else do I have another difference? This hydrogen's here, and then there's nothing there because it's double bonded to the oxygen. So when I move from here to here, what happens? We're losing the hydrogen. So beta hydroxybutyrate loses hydrogens. Well, what is loss of hydrogens? That is oxidation. So beta hydroxybutyrate loses hydrogens. That is oxidation. X-I-D-A-T-I-O-N, right? When we write biological molecules, a lot of times you're going to have another reactant. So this is just like saying beta hydroxybutyrate plus NAD plus yields oxaloacetate and NADH plus H plus. So tell me about the NAD plus. What is it doing? This is the reactant. This is the product. Gains hydrogens. So what is NAD plus doing? It's being reduced or undergoing reduction. Right? So identify the reactant oxidized and the reactant reduced. Did we do that? Absolutely. Good. Question? What are you coming with tomorrow? Thursday. Calculator and a pencil. I'll have a joke for you. Yeah, it's not going to be the largest portion of the exam. No.
It was gonna be like, it's like, I know it wouldn't be a lot, like, not.
Well, this is the end of the section. Didn't we finish the section? Yeah. So 1 through 4, chapter 5, sections 1 through 4. Yeah. Correct, but sections, chapter 5, sections 1 through 4 are on the exam. Yeah. Yeah, once you talk to them, just let me
I
know.
scheduled already. I put it for 10 in the morning.
Okay.
I just want to make sure.
That's great. I love those emails. Mhm. Sure.
Okay, so I like research all elections and stuff.
Okay.
Do you suggest like studying like class problems or
No,
just everything?
no. I suggest doing problems.
Like extra?
So like the end of the chapter, right? If there are some like, okay, I know I got dimensional analysis. You don't have to spend your time.
Right.
But other ones, I would. And at the end of the chapter, they're even and odd.
Okay.
I think it's the odd where the answers turn the page
And it has.
and the answers are there.
Okay.
So it's a really quick way for you to,
And I could get that through.
through your ebook.
Okay.
It's
So
in
like
your
what
ebook.
we have.
So watch, I'm gonna pull it up. I'm gonna show you.
You guys like.
Oh, let me- I'm
watched all
still running the
videos
Zoom.
and stuff.
Hold on, let me get the Zoom. Nobody else is on Zoom.